Hi there, and welcome back to our second video on equivalent equations. Firstly, let's have a think about what equivalence might mean. You may have heard about equivalence with regards to fractions. Let's see what it means with regards to equations. If we have an equation, we can create an equivalent equation by performing the same operation to both sides. For the equation 2y plus 4 equals 20, we could, for example, add 10 to both sides of the equation to obtain a new but equivalent equation. Let's do that now. We're going to add 10 to both sides of the equation. That means to the left-hand side and to the right-hand side of the equation. And of course we're going to remember that we can only add like terms. So on the left-hand side of the equation, I've got 2y plus 4, and I'm going to add 10 onto that. So that's going to become 2y plus 14. On the right-hand side, I've got 20, and I'm going to add 10 onto that, so I've got 30. So I have now a new equivalent equation which represents the same thing, looks a little bit different, but is equal in value to the previous equation. Now I can make lots of equivalent equations. I could subtract, for example, 7 from both sides to create another new equivalent equation. So let's do that. Take away 7 from both sides. What would I have on the left-hand side? Again, remembering my like terms, I can only take 7 away from the 14. So that will give me 7 here now. And on the right-hand side, 30 take away 7 will be 23. Why did I take away 7? No real reason other than I made that suggestion. Why did I add 10? Again, no real reason, but what we're going to be looking at soon is what would be good numbers to add or subtract, multiply or divide. Okay, so how do we create equivalent equations? You've seen me make 2 equivalent equations on the previous slide. 2 equations are equivalent if you can get from one to the other by repeatedly adding a number to both sides. You saw me do that with adding 10. Subtracting a number from both sides, well, we did that when we subtracted 7. We could be multiplying both sides by a number other than 0, or dividing both sides by a number other than 0. Or we could be swapping the left-hand side of the equation and the right-hand side of the equation over. There's an example here of an algebraic equation which has been simplified at each stage of the equation. So here you can see we've chosen to subtract 2 from both sides. I wonder why. Maybe it's got something to do with this number here. And we've ended up with a new equivalent equation, 5x equals 30. And then we've made that even a little bit simpler by dividing both sides by 5. Again, I'd ask you to question why we divided by 5, and maybe it's got something to do with the timesing by 5 there, until finally we've got a very, very simple equivalent equation at the end which actually solves the problem for us and shows us that x must have been equal to 6. Alright, so what do we know about equivalent equations so far? They help us to solve equations algebraically using algebra. They give us a method other than guess and check, which we used in the last video. They will be very helpful for us when the questions become more difficult, so we will need to learn how to use equivalent equations. And finally, when solving an equation, we're going to aim to make each new equivalent equation a bit simpler than the one before it. Right, let's have a look at a couple of questions here and see how we can apply our equivalent equations. Alright, so the first one is 4u equals 36, that's this one up here. So I'm going to create an equivalent equation which looks a bit simpler than this one, and I'm choosing to divide by 4. Why might that be the case? Because I'm using the inverse operation of timesing by 4, which is what this 4 is doing at the moment. So dividing both sides by 4, I'll end up with u on this side and 9 on this side, because 36, how many 4s is 9? This question I could have solved by inspection. I could have said 4 times what equals 36, and of course it's 9, but remember we're practicing how to use equivalent equations in this particular video. Alright, the second example here, b take away 5 equals 3. I'm going to make an equivalent equation here by plussing 5. Hopefully you're starting to understand that I am undoing what's sitting up here next to the b, and the opposite or the inverse of taking away 5 is adding 5. When I add 5 onto this left hand side, I've got b take away 5 plus 5, I'm going to end up with just b. And on the right hand side I'll have 3 plus 5, which is 8. Let's check, does that make sense? My answer of 8, does 8 take away 5 equal 3? Sure does, so I know my answer is correct. The third example, again using equivalent equations. Have a think about what we might do to undo our plus 9 here. I'm going to take away 9. And over on the left hand side, I'm going to have d plus 9 take away 9, which is just d. And on the right hand side, 2 take away 9, which is negative 7. And when I put that negative 7 back in here, negative 7 plus 9 equals 2. So again, I know my answer is correct. The third example, x over 10. Remember that means x divided by 10 in algebra. So to undo that, I will need to multiply by 10. When I multiply by 10, that has the effect of cancelling out the dividing by 10, as you can see over here. Of course, whatever I do to this left-hand side of the equation, I must do to the right-hand side to keep it equivalent. So I need to times this by 10 as well. What I'm left with is x is equal to 70. 7 times 10. When I put my 70 value in here, 70 divided by 10 equals 7. So again, I know my answer is correct. The final question on this page, negative 5c equals 30. So again, I'm looking for an equivalent equation which is going to make this simpler. In other words, I want the c by itself. I want to undo this negative 5. Now you have to ask yourself, what's the negative 5 doing to the c? It is multiplying. So we need to undo that. The inverse of multiplying is dividing. So we're going to divide by negative 5 both sides. When I divide this side by negative 5, those negative 5s cancel out. And when I divide this side by negative 5, 30 divided by negative 5 is negative 6, using my knowledge of negative numbers there. So there's some ideas about how to use equivalent equations to solve them. Alright, what about equations which will take more than one step to solve? How would we approach those? Firstly, we've got to be pretty clear on our BIDMAS laws, because we'll be using those and then undoing those. So we do have to be very clear on BIDMAS. Secondly, as a general rule, the numbers which are closest to the pronumeral are usually the last numbers to be dealt with or undone. That means we need to start undoing the operations which are furthest away from the pronumeral. So let's have a look at some examples of how we can put this into practice. Okay, we've got 3 equations here. They are all 2-step equations. That means we're probably going to have to take 2 steps to solve them. On the previous slide we said let's consider removing the things that are furthest away from the pronumeral. So in this particular case, I'm going to be looking at removing that 4. So I want an equivalent equation which has the effect of getting rid of that 4. At the moment it's plussing, so I'm going to take away 4 from both sides. What am I left with? Just 2p on this side and 16 on this side. Now I want an equivalent equation which just leaves me with a p at the end. So I would need to undo that timesing by 2 by dividing by 2. What am I left with? P. And over on this side, 16 divided by 2 equals 8. Let's just substitute our answer back into the question. 2 times 8 is 16. 16 plus 4 equals 20. So that's great. I know my answer of p equals 8 is correct. The second equation over here, on this side here, we could use the idea, if we wanted, that we can make an equivalent equation where we move the left-hand side over to the right-hand side and the right-hand side to the left-hand side. We don't have to do that, but I know from experience that a lot of students seem to like the unknown being on the left-hand side. So we can do that, and we've still got exactly the same equation. All right, again, I'm trying to make this particular equation a little bit simpler looking, and I'm going to do that by removing that 12. At the moment we're subtracting 12, and the opposite to that is plusing 12. So I'm going to end up with 5u on this side and 45 on this side. So I could be using my idea of inspection, 5 times something equals 45, to work out that u must be equal to 9, or of course I could again use my equivalent equations, undoing multiplying by 5 by dividing by 5. When I divide this by 5, the 5's cancel and I get u. When I divide this side by 5, 45, how many 5s is 9, which is what I said a little while ago. Again, I could substitute it back in. 5 times 9 is 45. 45 minus 12 is 33. I know my answer is correct. Okay, the final example down here, just a little bit trickier. 16 minus 3a equals 22. Again, I'm going to have a go at removing the things that are furthest away from the a. So in this case, it will involve getting rid of the 16. Is this 16 positive or negative? The sign in front of it will tell us, and if there's no sign, of course we know that it's positive 16. So the first thing I'm going to undo is that plus 16 by taking away 16. And of course, whatever I do to the left-hand side, I need to do to the right-hand side. What I'm left with now is negative 3a is equal to 6. One more step, because remember all of these are two-step equations. I want to get the a by itself, and I'm going to do that by dividing by negative 3. And whatever I do to the left, I do to the right as well. So I'm left with a on this side, and 6 divided by negative 3 is negative 2. So in this case, if I put negative 2 up in here, substitute it in, it should give me an answer of 22, which it does. Okay, so there's plenty of examples here that you should have been copying down. So now that you've done that, write a couple of sentences which summarise what this video was about, and of course, write down any questions that you've got and bring those into the next class. I'm sure you'll have 1 or 2 questions. Okay, see you next time. Bye.